You build ASI-Arch. It doesn't just search, it invents. You set it loose on neural architectures. It runs 1,773 experiments, burns 20,000 GPU hours. You check the results. 106 state-of-the-art linear attention models. None like anything humans designed. You compare to old NAS. It was stuck in human-defined boxes. It dreams up new concepts, codes them, tests them. All alone, you look at the patterns. They're not just better, they're alien. Principles no researcher saw coming. You plot the data. More computation, more breakthroughs. A straight line, no plateau.
Research progress isn't limited by human brains anymore.
It's limited by how many GPUs you plug in. You open source everything, the code, the architectures, the thought traces. You step back, it's not just a tool. It's AI starting to build better AI on its own terms. Someone says, but it's just optimizing. You show the emergent design. They say, but humans still lead. You point to the scaling law. They go quiet. You realize you didn't build a search algorithm. You build a self-accelerating engine for AI to invent its own future. Okay. Let's unpack that. Because, I mean, wow, you know how we humans, right? With our perfectly squishy, definitely coffee-fueled brains, we toil for months, sometimes years, just trying to design maybe one, if we're lucky, two really groundbreaking AI architectures, sweating over these like obscure papers, debugging cryptic code, burning that midnight oil, hoping for some kind of aha moment. Well, it seems the robots kind of looked at our pace and thought, maybe just a tad inefficient. So today we're doing a deep dive into ASI-Arch. It's this really revolutionary system. Came out of the SII-GAR collaboration. That's Shanghai Jiao Tong University, SII-GAR, and TapTap. And their mission, like we just heard, is basically to smash this thing they call the human-limited bottleneck in AI research. Because let's be honest, human-only research, taking, 2,000 hours per model? It just doesn't scale, does it? And this isn't just about, automated optimization, finding the best version of our ideas. No. This feels like a huge paradigm leap, a shift into automated innovation. We're literally talking about AI running its own scientific research program, designing the next generation of AI on its own.
Yeah, and that phrase paradigm shift, I think that's exactly right. It's profound. Historically, AI systems have always been tools for us, for human researchers. But ASI-Arch, it really does operate more like an AI scientist in its own right. It's actually built to handle the entire research process by itself, from like hypothesizing totally new architectural ideas.
Ideas it comes up with itself.
Exactly. Then implementing them, actually writing the code,
Yeah.
training them, and then really rigorously testing and validating their performance. It's not just some fancy selection algorithm picking from a menu we gave it. It's a fundamentally different way of thinking about discovery in this field.
And the scale, the sheer scale of what it pulled off is just mind-boggling. What was it? 1,773 autonomous experiments.
That's right.
Burning through 20,000 GPU hours.
Right.
Which is a lot of compute.
A significant amount, yes. And the result, you get this staggering number, 106 novel, state-of-the-art linear attention architectures.
And here's the real kicker, the part that really makes you sit up and pay attention. None of them look like anything humans have designed.
That's the key point. It's being described as potentially an AlphaGo moment for discovering model architectures.
Okay. Like AlphaGo's famous move 37 against Lee Sedol, the move that seemed wrong but turned out brilliant.
Precisely. Just like that move revealed strategic depths in Go that humans hadn't seen. ASI-Arch's discoveries, these architectures, they seem to demonstrate emergent design principles that systematically outperform our best human-designed models.
So it's not just finding the best path within the map we drew.
It's drawing completely new maps, designing outside the box we didn't even realize we were in, creating designs based on principles, as the intro said, that no human researcher saw coming. They look alien.
Okay, so if it's acting like an AI scientist, how does it actually work? What's under the hood? How is it structured to allow for that level of, autonomous innovation and discovery?
Well, it's designed as this really quite sophisticated closed-loop system. Think of it almost like a multi-agent framework, like a mini self-contained research department maybe, with different specialized AI agents collaborating.
Okay, different agents, like what?
So first you have the researcher module. You think of that as the creative engine, the brain maybe. It proposes new architectures. And critically, it doesn't just learn from old human papers, it learns from its own past experiments, its successes and its failures.
So it builds on its own findings.
Exactly. Then there's the engineer module. This one takes those abstract ideas from the researcher and turns them into actual executable code. It handles the training process too. And here's something really clever. It self-revises.
Self-revises? What does that mean?
It means if it hits a bug, a coding error, It doesn't just stop a crash. It analyzes the error log, figures out what went wrong, tries to fix its own code, and then runs it again.
Wait, it debugs itself.
It debugs itself.
Hmm.
Imagine having a research assistant that learns from its own coding mistakes and fixes them on the fly.
Okay, that level of self-correction is...
Yeah, that's revolutionary. It's not just, like you said, throwing spaghetti at the wall and seeing what sticks.
Right, and it doesn't stop there. There's also an analyst module.
What does that do? The analyst is crucial. It takes all the results from all those experiments, synthesizes them, tries to figure out why something worked or didn't work, and derives new insights. And it feeds those insights back to the researcher module. So the whole system gets smarter over time.
A learning loop.
A very powerful learning loop.
Yeah.
Plus, there's a cognition base. Think of it as a highly curated knowledge library, built from, I think, nearly 100 seminal human papers specifically on linear attention. So it has centuries of human expertise distilled down.
Okay, so it has our knowledge, but it also generates its own.
Precisely. And one more component, they even use a large language model, an LLM, to act as a sort of qualitative judge.
A judge? Why?
To help prevent something called reward hacking.
Ah,
Yeah.
where the AI finds a clever loophole to score high on a metric without actually being good or useful.
Exactly that. The LLM provides a more nuanced assessment, pushing the system towards genuine innovation, not just optimizing for a number.
So it's constantly learning, adapting, coding, testing, analyzing, even judging its own work qualitatively. That's
Yes.
incredibly advanced. And this leads to something you mentioned, something that honestly kind of keeps me up at night. In a good way, I think. ASI-Arch apparently established the first empirical scaling law for scientific discovery. That sounds huge.
It is huge.
Yeah.
This might be the most profound takeaway from the whole project.
So what does it actually mean, a scaling law for discovery?
It means they found a direct linear relationship, like a straight line on a graph, between the total amount of computing power used
Yeah.
and the number of state-of-the-art architectures the system discovered.
Wait, seriously, so more compute equals more breakthroughs, predictably?
Predictably, at least within this context,
Right.
it suggests that architectural breakthroughs, at least for linear attention models, can now be computationally scaled.
Wow. So we're moving from research progress being limited mostly by, human brain power, human creativity, which doesn't really scale easily.
Right. To a process where progress can potentially be accelerated just by adding more compute, more GPUs.
Yeah.
That phrase from the intro, more computation, more discoveries, it isn't just a slogan. They actually demonstrated it empirically.
That fundamentally changes the game for AI research, doesn't it?
It really does.
Yeah.
It changes the whole equation for what might be possible and how quickly we might get there.
It's astonishing. I mean, for years, every big AI breakthrough felt like this Herculean effort, a bit of luck, maybe a single genius having a moment. To think it could become a predictable function of compute. Yeah. Paradigm shifting is the right word. But okay, does this mean we can just throw GPUs at any scientific problem and expect breakthroughs? Or is it more specific?
That's a very important distinction to make. Right now, this scaling law specifically applies to neural architecture discovery in the domain ASI-Arch was working in linear attention. It strongly suggests that for this type of research, the main bottleneck isn't human ingenuity anymore. It's computational resources.
So research labs, universities, companies, they could potentially speed up their AI architecture R&D just by scaling their compute clusters.
Potentially, yes.
Yes.
Instead of just hoping for the next human insight, they can invest in compute to drive discovery more predictably. It makes that part of research feel less like an unpredictable art and more like a scalable science.
Okay, let's talk about the designs themselves, these 106 novel architectures. You said they're not just incrementally better, they show emergent design intelligence. That sounds cool, but what does it actually look like? How do these alien principles show up in the models? And maybe just a quick reminder for listeners, linear attention models are important because they're efficient for long sequences, right? Like in big language models.
Exactly. Crucial for handling long contexts efficiently.
Okay.
So examples of this alien ingenuity. Well, humans often design AI processing paths to be kind of sequential, or maybe pick one best route using something like softmax. But ASI-Arch came up with models like fusion-gated FirNet. This one uses parallel sigmoid gates instead.
Okay. What does that do differently?
Well, instead of forcing a choice of just one path, sigmoid gates allow the model to intelligently activate multiple information pathways at the same time. It allows for a richer, more complex flow of information. It's like having multiple specialists contribute simultaneously instead of just one.
Ah, interesting. Okay. Any others?
Yeah, or take hierarchical gating with dynamic floors. They call it higher gate net. This architecture has a clever mechanism to make sure important pathways never completely shut down, even if there's noise or uncertainty. It maintains a baseline activity.
So it's more robust.
Seems to be. These aren't just small tweaks on human ideas. They feel like fundamentally different ways of structuring computation. They often lead to better performance, especially on tasks needing long-range reasoning. And yeah, the internal logic sometimes looks quite different from how a human might approach it.
And it's interesting you noted it's not just about making models bigger and bigger, which seems to be a trend sometimes.
Right, that's a key observation from the analysis. ASI-Arch didn't just stack more and more complex components. Most of its top designs stayed within a reasonable parameter range, around 400, 600 million parameters. There wasn't a trend towards just bloating the size.
It showed architectural discipline, even without us telling it to. That's smart.
It implies the performance gains are coming from genuinely smarter, more efficient structures, not just brute force scale.
Is there any worry, though? If it's designing things humans don't fully understand, could it find solutions that are efficient but maybe opaque? Or maybe have unintended consequences?
That's always a valid question with highly autonomous AI systems, absolutely. But in ASI-Arch case, that comprehensive feedback loop, including having that LLM act as a qualitative judge, helps steer it. It guides it towards solutions that are not just numerically optimal, but also robust and hopefully more interpretable, or at least innovative in a good way. The fact it didn't just inflate model size suggests it has some kind of sophisticated internal sense of good, efficient design.
So where did these amazing designs actually come from within the AI? Was it just remixing human knowledge from that cognition base? Or something more? That intro rap mentioned thought traces. What are those?
Yeah, that's really key to understanding if it's truly innovating. The analysis in the sources is fascinating here. They found that while all the architectures it generated initially drew heavily on cognition, the distilled human knowledge, the top performing ones, those 106 state-of-the-art models, showed a really significant increase in reliance on what they call analysis.
Analysis meaning its own findings.
Exactly, meaning they were drawing much more heavily on the system's own empirical results, its own experiments, the insights it derived itself from trying things out, failing, succeeding. Those thought traces are essentially the detailed internal logs. The record of the AI's reasoning, its decision process, the raw data of its own scientific journey. It suggests that true breakthroughs, whether by humans or AI, don't just come from recycling old knowledge. They come from actively exploring, synthesizing new data, discovering new principles through experimentation, pushing beyond what was known.
So, okay, let's try and wrap our heads around this. What does this all mean for us, for the future of AI? We've seen ASI-Arch, this AI system, autonomously discover 106 novel, genuinely state-of-the-art linear attention models. That alone is huge. It's fundamentally changed how we might find new AI architectures. And we've talked about the maybe even more profound part, this scaling law for scientific discovery it established. The idea that research progress, at least in this area, can shift from being human-limited to being compute-scalable. It really feels like we are witnessing AI starting to build better AI on its own terms, like a self-accelerating engine for innovation.
And if you connect that to the slightly bigger picture, where does this trajectory lead? The sources briefly mention potential future systems, concepts like AlphaVolve or maybe Darwin-Gödel machines. These are theoretical systems designed to literally rewrite and improve their own code iteratively.
Whoa. So think about it. When AI starts not just learning from the data we give it, but truly inventing beyond our current understanding.
And then starts building the next version of itself based on those inventions, possibly at a speed we can barely track. What does that mean for our role in all this?
Yeah.
Are we, just the people who laid the first brick? And now the building is going to start constructing its own skyscraper, adding floors faster than we can even count?
That's a sobering thought. It raises a really important question, I think. When AI becomes its own lead researcher, maybe even its own engineer.
What new frontiers of knowledge will open up? And maybe what new questions will emerge about our own place in the whole process of discovery?
Definitely some powerful thoughts to chew on there. This field is just moving incredibly fast. Understanding these kinds of shifts like ASI-Arch and thinking through the huge implications, it feels more critical than ever. So yeah, stay curious, everyone, and keep digging into these fascinating developments with us, and definitely never stop questioning what might come next.